Good afternoon, class. Here's practice test number 5 of elementary statistics, module 5, covering chapters 10, 11, and 12. Chapter 10, correlation and regression. Chapter 11, goodness of fit and contingency tables. Chapter 12, analysis of variance. And now here's chapter 10, correlation and regression. So as always, there's a pledge when you take the exam. So reminding you, I pledge on my honor that I will neither give nor receive unauthorized assistance, so on and so forth. As always, you may use a formula sheet, tables, and a graphing calculator. So here's chapter 10, correlation and regression. Given the sample data, find the value of the linear correlation coefficient R. Test the claim that there is a linear correlation between the two variables. And there are a couple of methods we're going to discuss, and alpha is 0.05. We're going to find the regression equation and find the predicted value of y when x is 2. So here's the data, and let's discuss the concept first. Number one, scatter plot and the strength of linear correlation R. A scatter plot is a graph of the ordered pairs x, comma, y. So you have a bunch of pairs, and you put them in to a grid. X is the independent variable, y is the dependent variable. So when you do that, it may look like this. And what we are looking at is the following: distinct straight line or linear pattern. We say that there is a positive linear correlation between x and y, since as the x value increases, the corresponding y value also increases. If there is a strong positive linear relationship between the variables, the value of R will be close to +1. And that means 0.7 or larger. So positive correlation, or in this case, negative correlation. In other words, distinct straight line again, or linear pattern. We say that there is a negative linear correlation between x and y, since as the x values increase, the corresponding y variables, the y values decrease. If there is a strong negative linear relationship between the variables, the value of R will be close to -1. In other words, negative 0.7 or smaller. And R is between -1 and 1. And there is no correlation, as the dots are all over the map. In other words, no distinct pattern, which suggests that there is no correlation between x and y. More specifically, at this point, no linear correlation. So, as I mentioned, rho, which represents the linear correlation value, goes from -1 to 1. Okay. A 0 means no linear correlation. Close to 1 means strong positive linear relationship or correlation. From -0.7 to -1, also strong in a negative direction. Correlation doesn't imply causality. Just because two things happen at the same time or seem related doesn't mean that one causes the other or is between -1 and 1. That's for a sample, and rho is the population correlation as far as we are concerned. And now, here's a very common example that is used to explain this concept. Ice cream sales and drowning incidents both increase in summer. Correlation, these two trends go up together, yes. But there's not causation. Ice cream does not cause drowning. Instead, a third factor, hot weather, leads to both. And that's something we want to make a note of it and understand what's going on. So the linear correlation, okay, in this case, has a coefficient R for sample and rho. This is for sample, and rho for a population. Want to be comfortable with the concept, as I mentioned before. So let's do the math for this question. So first and foremost, we have the pair 1, 2, 1, 8, 3 comma 6, 5 comma 4. I want everybody to understand that there are only 4 pairs. That means n is 4. So we have 4 pieces of data. Why do we have such a small data? Because I want to show you how it's done by hand. Normally, you don't do it by hand. The formula is pretty complicated. R is n summation of xy minus summation of x times summation of y over the square root of the product of two things, n summation of x squared minus summation of x quantity squared times n summation of y squared minus summation of y quantity squared. As you can see, it's pretty involved. So having said that, we are going to write x, y, and then we need x times y. We need x squared. We need y squared. So let's write x's, y's, and then we have x times y, which means multiply these two. 1 times 2 is 2, 1 times 8 is 8, 3 times 6 is 18, 5 times 4 is 20. So that's this column. Then we need x squared. That means 1 squared is 1, 1 squared is 1, 3 squared is 9, 5 squared is 25. Then we need y squared. 2 squared is 4, 8 squared is 64, 6 squared is 36, 4 squared is 16. Then we need all the summations. So we're going to add these numbers in the x column. We call it summation of x. So 1 plus 1, 2 plus 3, 5 plus 5 is 10. And we do exactly the same thing for each column. Summation of x, summation of y, summation of xy, summation of x squared, summation of y squared. We do all of it. We do that so we get ready for this formula. Again, as you can see, it's a little bit involved. Having said that, so R is equal to n, replace it with 4, here, here, and here. Summation of xy is 48. So 4 times 48 minus summation of x10 times summation of y20. Then at the bottom, we have, as I mentioned, 4 here. Summation of x squared goes there, 36 minus summation of x, which is 10 quantity squared. Then n is again 4. Summation of y squared is 120 minus summation of y 20 squared. So you just plug in. Again, you have this in your formulation. We end up with the following, and here's the answer. But if we were to use technology, of course, and you can use technology, obviously, we're going to clear list 1, and then we are going to put x and y into L1 and L2 first, clear in case there is something in there. So you clear not only L1, also L2. So you have L1, 1135, and that's all the x's. L2, maybe it's easier to go this way, 2864. And now you run the linear regression t-test, It's going to put L1 for x, L2 for y, and you can change it if that's not what you have used. Okay. Rho is not equal to 0. You run it. As you can see, there's an arrow. You continue, and we are going to come back to this. But for all of these calculations, all we are looking at is this number. And take a look at ours. 1, 2, 3. If we stop here, 4 changes to 5 because next to it is 8. As you can see, that's what we wanted. Although it has done more because we need to do more, but this part is the answer to this question. So having said that, let's do test of hypothesis. So test the claim that there is a linear correlation between the two variables, and use both methods. We're going to discuss the methods. Alpha is 0.05. From the previous page, remember, n is 4, and we found R to be negative 0.135. So we're going to write it here. So we're going to write the null and alternative hypothesis, H0. This is rho, a Greek letter rho, is equal to 0. And then rho is not equal to 0 is H1, which makes the two-tailed test, and that is the claim. So this means correlation, this means no correlation. That's really the bottom line. So we're going to run the test statistic for both methods. For the t-test is R minus mu sub R over square root of 1 minus R squared over n minus 2, and mu sub R is this one class, and as far as we are concerned, it's always 0. But before we continue, please look at this formula. and convince yourself it's the same as this one. It's just a different way of writing that this one is identical to this one. And I'm mentioning it because it depends on the text. They may write it in this format or in this format. Of course, we are assuming this is 0. That's why. If it's not 0, they are not identical. So plug in. We have everything. We have the R, which is negative 0.135. And we have the N, which is 4. And we end up with this number. So that's the test statistic. Let me erase my work, by the way. That's, again, I wanted to show you that. That's the test statistic if we go with the t-test. But if we are going to go with the second method, okay, that we uses the Pearson correlation coefficient, R is the test statistic, and R is already calculated. The next one is distribution, CV, critical value, RR, rejection region, NRR, non-rejection region. That's what we get with the critical value. Critical value comes from the t-test choice of alpha, which is 0.05. Alpha is 0.05. Degrees of freedom, it's n minus 2 here because we have two sets of data. N minus 2 is 2. And now if you look up the table, okay, you come up with the answer. And I'm going to remind you, as far as the table, the t-test, how we arrive at it in the next page. So we get plus minus 4.303. That's as far as the first method, which is the t-test. Of course, we have decision making. For this method, it comes from a table, okay? When n is 4, alpha is 0.05, use R, CV from Pearson correlation coefficient table. Again, I will show you that one. And that gives us plus minus 0.950. So we are going to draw a bell-shaped with these two values, negative and positive 4.303 as the critical points, and test statistic negative 0.135 is negative 0.1927 is way in between. For this one, we just draw a line segment or a number line from the rejection region negative 0.950 to the left and positive 0.950 to the right. And this R also is in between. So I hope you see this one. This number is in between. Okay. Negative and positive 4.303. This one from the Pearson correlation coefficient table, and negative and positive 0.950. Those are the critical values. And negative 0.135 is the statistic is in between, therefore fail to reject H0. Now, H0 means there is no correlation. That's really the bottom line. So the claim becomes false because it belongs to H1, and there's no linear correlation between the two variables. So if we go with H0, no correlation. If we go with H1, there is a strong correlation. I want to remind you how we use, again, the table, the t-distribution, and I'm going to discuss this one as well. So first and foremost, as far as the technology is concerned, we did this in the previous page, and I want to show you a couple of things here. Number one, this value test statistic, negative 0.192450. It's very close to what we have. One might say, okay, why aren't they identical? Because remember, we did the rounding for R and we stopped at 5, but they don't. Okay, that's the reason. Now, the next one, this one is the p-value, everybody. And the p-value is way larger than alpha of 0.05. Same decision. Fail to reject H0, no linear correlation. Okay, it's very straightforward, everybody. And now, as far as how we came up with the values here for the table, reminding you of the t-test where alpha is 0.05, degrees of freedom is n minus 2 or 2. In the left column, you locate degrees of freedom. And at top, a 0.05 area in two tails. Intersection gives you this number, and you're going to write plus minus because it's a two-tail test. This is a Pearson correlation coefficient. The very first thing you have to be careful with the alpha. So n is 4. In this column, you find 4. Alpha is 0.05. In these two columns, you find alpha of 0.05. This one, not this one. And intersection of the two is this number, 0.950. Because it's a two-tail test, you're going to write critical value ER is plus minus 0.950 as we looked at it in the previous page. Let's continue with the rest of the question. I'm going to come up with the regression equation. Again, I want to show you formulas that can be used because we already have worked very, very hard to get all of those. Reminding you, n is 4, r is negative 0.135. Summation of x, summation of y, and the rest of them are calculated. So the formula indicates that we go either with y hat is b sub 0 plus b1x, or y hat is a plus bx, depending upon what technology you use. And I want to remind you y equals mx plus b. That's the meaning of it, okay? So b1 represents the m here, b represents the m. So y equals mx plus b, the point slope format of a line. Having said that, we need the m and we need the b. And so let me erase my work again. And so if we go with this one, b1 is taking this formula and we have everything. So let's plug into this. N is for summation of x, y is 48 minus summation of x, summation of y, 10 times 20, over n summation of x squared is 36 minus summation of x, 10 quantity squared. So you can calculate it. And again, with just a couple of decimals, in this case, 3 decimals, negative 0.182. That's B1. What about B sub 0? Is y bar minus B1 x bar. So we need to calculate y bar. We already have summation of y. I hope you see that y bar is summation of y divided by n. Summation of y, we've already added them up to 20, divided by n, which is 4, and we get 5. And over here, we need x bar. So summation of x over n. Summation of x is 10 over 4, and that's 2.5. Now we have y bar minus b1 x bar. That is y bar 5 minus b1. Now for b1, I'm going to use actually what I have in more decimals and then times 2.5. So I highly recommend you do that. Get this number. And therefore, y hat takes the formula negative 0.182x plus 5.455. I want to remind you, we did run the linear regression test in the beginning. And what do we find here? Okay. A plus bx. See, this is the formula they use in TI calculator. Here's A. Here's we notice A is the constant or the y-intercept 5.4545, and it continues indefinitely. So if you stop here, it changes to 5. And this one, if you stop here, it changes to 2. And that's what we have here. So you have to round it to a certain degree. So find the best predicted value of y when x is equal to 2. There are two things. Either they have a correlation or they don't have a correlation. If we didn't find any correlation, then we use the y bar. If there is a correlation, we plug in. So no significant linear correlation. The best predicted y value is y bar. If you recall that this is the p. So r is negative 0.135. Therefore, y bar, which was 5, is the answer. And remember, this is the p value, 0.865, much larger than alpha 0.05. Don't reject or fail to reject H0. there's no linear correlation. I'm reminding you of what we have done already, which means if there's no correlation, you use Y bar. If there is a correlation, you plug it. A researcher is studying the effects of testosterone injection on different lab mice. She controls the concentration of testosterone injected into mice and measures their metabolic rates. Analyze the following data set. Will you be running a correlation or regression? Find the value of the linear correlation coefficient R and test the claim that there is a linear correlation between the two variables X and Y, alpha equals 0.05. Obviously, we're going to run regression. Here's what's happening. We run regression since she controls the concentration of testosterone injected into the mice and measures their metabolic rates. So it's a controlled environment, so it's a regression. So if there is a correlation, then that has got to do with the controlled substance, in this case, testosterone. So we have the amount of testosterone and the metabolic rate, Y, is a function of X or not. That's what we are looking for. And so obviously, we're not going to do this by hand. We are going to run some sort of a technology. For example, if we run Excel. First, write down H0, rho equals 0. There is no correlation between the concentration of testosterone in mice and their metabolic rates. HA, H sub A or H sub 1, remember that? Rho is not equal to 0. It's a two-tailed test. There is a correlation between the concentration of testosterone in mice and their metabolic rates. And that is the claim. That's what we are checking. So if you run Excel, it gives you this, it gives you this, R is this, R squared is that, and all of the above. And we are going to see what each one means and taking it from there. So obviously we want the coefficient R. R is 0.9934. As you can see, just it's extremely large. It's very close to 1. So you should have an idea of what's going to happen. By the way, alpha in most researches is 0.05, unless something that has got to do with medicine and you want to be very careful, perhaps you make it smaller. But normally 0.05. So having said that, so that's R, and we've run this. So I'm going to remind you we have this. N is 17, by the way, there were 17 pieces of data. Excel gives us those values and those values, and reminding you the very first step, H sub 0 rho equals 0, H sub A rho is not equal to 0. And those are the two parts that want to start. And the next one is test statistic. Test statistic, there are two ways to do it. The t-test, okay, or the Pearson correlation table. Here's the formula, reminding the formula, and it's given to us. This is the number, everybody, T stats, okay? This number, 33.635. It's been already calculated. As far as the second method is concerned, R was 0.9934 in case anybody wants to know, okay? So let's go with the second part. Remember, we go with the critical value, but if we have run technology, it has given us p-value. So based on the t-test, the p-value is this number. Okay, remember, alpha is 0.05, so this is 0.05 divided by 2. This is 0.05 divided by 2. And the p-value is this number. And e minus 15 means 10 to the power of negative 15. So you write this number times 10 to the power of negative 15. And that is because the test statistic is way into the rejection region. I can't even locate that. It's, it's way to the right. And so the p-value 1.5316 times 10 to the power minus 15, which means you have the decimal here, you go to the left by how many spots? 15 decimals. For second method, we use R here, which is 0.9934. And then from the Pearson correlation table, any 17 alpha is 0.05. And from the table, you can look it up, we get plus minus 0.0456. In other words, if we want to go with this number line, we have the negative number, positive number, and we want to locate this one is way into the right side of the 0.456 critical value rejection region. So test statistic of 0.9934 is way into the rejection region. Therefore, we make the same decision in both cases. Reject H0. Reject H0 since the p-value, which is this number, is less than alpha. By the way, this p-value is almost zero, everybody. Again, point, move it to the left 15 times because it's minus 50. So if you're rejecting H0, we go back to the very first step. Where does the claim go? Claim is here, belongs to the second part. Therefore, the claim becomes true. And there is a significant linear correlation. So there is a significant linear correlation between the two variables. Therefore, we conclude that there is a significant correlation between the concentration of testosterone in mice and their metabolic rates. Since this is a regression study, the significant slope, this one, it's almost 200, 199.05, almost 200, suggests that the increase in concentration of testosterone in mice causes increase in their metabolic rates. So that's very straightforward, everybody.